Okay, so we've been talking chapter 10 here, talking about solutions last time. Um, we talked about, again, the idea of what a solution is, that there's a solute, which is the smaller part of a solution. There's also the solvent, which is the larger part of the solution. And obviously, both of those things together make up a solution. Solution is a homogeneous mixture, looks the same throughout. When you do that, it's the thing that gets the AQ symbol next to it. And as we talked about, I think last time, and probably a number of times as well, again, the difference between AQ and L. AQ basically means that you took something and dissolved it in a liquid, like you took some sodium chloride and dissolved it in some water, while something with an L is just a pure liquid by itself or a pure substance by itself. So something just like water by itself would get that L sort of designation. We also talked about sort of solubility and miscibility and how solutions sort of mix together and when they don't mix together. And really, a lot of that does involve those intermolecular forces that we talked about in the previous chapter. Basically, we had our dipole dipole, our hydrogen bonding, and our dispersion forces, where dipole dipole and hydrogen bonding are for polar molecules, while dispersion forces are really for our non-polar molecules. And ultimately, what we sort of talked about last time was the idea that what really makes something sort of soluble in each other is the ability to sort of interact really well with one another. And the way they're able to interact really well with one another is that they both are using sort of the same intermolecular forces. So if you have something that uses dipole dipole sort of mixing with something else that's using dipole dipole forces, you are going to tend to get something that's going to mix and perhaps make a solution. Well, if you sort of have something that's using dipole dipole and something that's maybe using dispersion forces, you're not going to get a long-term way for those guys to basically interact with each other, and you're really not going to get a solution to be made. They're not going to typically be soluble in each other. And that brought up the idea of what we talked about of like dissolves like. So again, things with similar intermolecular forces are going to be soluble in each other. So if you have something that's ionic, it works really well with something that's polar. If you have something that's polar, it works well with something that's polar as well. And also, nonpolar and nonpolar work really well together. But again, if you sort of cross over, as we talked about, taking something that's polar and something that's nonpolar, you are going to run into trouble because of those really differences in intermolecular forces. So I think the example that we saw was like something like oil and water. Oil is pretty much all carbons and hydrogens and nonpolar, going to mainly be using dispersion forces, not going to play really well with water, which is polar, has the ability to hydrogen bond, and is going to want a hydrogen bond. So those two things really have no, like I said, long way to maintain those interactions. We also talked about, I think, the idea of a saturated solution. Saturated solution is really a solution where you've pretty much at a particular temperature hit the maximum amount of solute that you could dissolve in that solution. Um, Solubility really is based on temperature, so it does change with temperature. Um, we also had an unsaturated solution where you pretty much haven't hit that point yet. So if you took more of the solid, you could continue to dissolve it until pretty much you hit the saturation point and that saturated solution at that point. And at the end there, I think we saw a supersaturated solution, which is typically made by starting with a saturated solution. You typically get heated up, and as you heat it up, that allows more solid to dissolve. And then you typically cool it back down. When you cool it back down, you now have way too much solid dissolved in that solvent, and it makes it a very unstable solution. As we saw, kind of talked about at the end last time, you literally can just take one small little crystal, whatever you dissolved in there, and it basically will take all of this solid out of the solution. You can kind of see it almost coming out of the solution, going from really a solution to something that is solid. Any questions on any of that stuff we talked about it last time? Okay, so I think this is where we sort of left off. We are talking about also some effects on solubility. So the pressure and effect on sort of the solubility of gases. So as we have sort of an external pressure, has a very high effect on the solubility of gases, especially sort of in the liquid part. So sort of our soda example that we were sort of talking about the other day as well. Um, when we have a soda, again, before you open it, you have a lot of pressure, And in that situation, we have a lot of the CO2 molecules dissolved in the liquid part of the soda. Obviously, as we talked about, if you pop the top there, you're going to release the pressure. That's going to allow those CO2 molecules basically to escape the liquid part. And as we also talked about, you also give it sort of an escape route. They can kind of go out and escape the can is in or the bottle is in. And also why when we come back after a while, as we talked about, it kind of is a little bit flat at that point. And this relationship between sort of concentration and pressure is what is sometimes referred to as Henry's law, and it basically states that the solubility of a gas in a liquid is proportional to the pressure of the gas over the liquid, and this is sort of its law right here. C is concentration, which is basically molarity. K is a constant, Henry's law constant, and it is specific for each sort of substance. So there is a different sort of Henry's law constant depending on the gas that you're dealing with. We'll see a table here in just a second, but it's basically a table value that you could kind of look up again for whatever substance you're dealing with. And P is pressure, and it's usually here in atmospheres as well. And we could use this to figure out things like the pressure we would have to sort of keep a gas to maintain a certain concentration, or vice versa. If we want to sort of maintain a certain pressure or concentration, or certain concentration to maintain a pressure. Here is a table of some of those guys, and again, as you can see, depending on sort of the gas you're dealing with, you will have a different sort of constant value, and that's why the pressure usually needs to be in atmospheres, again, because that's usually what the units are for Henry's law. Also, you can see here concentrations and molarity, so that's why usually concentrations and molarity as well. Obviously, like any table, you should always look at the units in those tables, because depending on where you look at it, may have different units. Here's a much prettier picture of what I drew, but same idea here. So obviously, as you can see, before you pop the top there, there's a lot of pressure. You see a lot more of the CO2 molecules dissolved in the liquid part. Again, as you pop the top, that's going to release the pressure, going to allow those gas molecules really to escape the liquid part, and obviously fizz out the top part there that we're probably familiar with as well when we've opened the soda. So sometimes, in addition to that law that we just saw there, which is C is equal to KH times P, and, and instead of C, sometimes people will use S, and S stands for the molar solubility, which is essentially molarity as well. So this is sometimes people will use S in place of the C, and it's basically the same thing. It's really molarity. If you take 200B, you'll see that S up here again, and that's sort of what it refers to as that molar solubility. So let's take a look at sort of a calculation involving this. We want to know what pressure of CO2 is required to keep the concentration of CO2 at 0.12 in a soda at 25 degrees Celsius. So we can use our sort of formula here. We have our C is equal to KH times P. Again, we would look up our value for KH in that table. I think they're going to put it there for me. Perfect. So our KH value is 3.4 times 10 to the minus 2. We're looking for the pressure. So we'll take the pressure is equal to C divided by KH. So our concentration, we want to keep it at 0.12 molar. Our value here, specific for CO2 gas. Molarities will cancel each other out, and it looks like we hit something like 3.5 atmospheres as our pressure that we need to basically keep our concentration of CO2 in our soda, where it needs to be, so it doesn't obviously go flat in that particular case. That is obviously much higher than sort of standard pressure, which is 1 atmosphere. So it's basically 3 times or so as much as standard pressure that you got built up there in your soda can. Any questions on Henry's law? So that's sort of the calculation for what we were talking about in terms of pressure and concentration of gases and liquids. Okay, so we're then going to talk about some concentration units, and some of these I believe we've talked about. So we'll kind of go over some of these a little quickly, just as a reminder of some of the ones that we talked about here a couple of chapters ago, I think. We did talk about percent mass to mass, which is again our mass of our solute over our mass of our solution times 100%. We also, I believe, talked about some other mass units. We talked about percent volume to volume, which is our volume of solute over volume of solution times 100%. Remember that the mass of the solution, especially for this first one here, is really important. You do want to make sure that you get both of those guys in there. Again, a lot of times they are given to you sort of separate in terms of the mass of the solute and the mass of the solvent. There's also percent mass to volume, which is again our mass of our solute divided by the volume of solution times 100%. And remember that, if you had, say, a 4.5% by mass solution of sodium chloride, you can use it as sort of a conversion factor. You could say you have 4.5 grams of sodium chloride in 100 grams of solution, or again, the opposite there, 100 grams of solution, you have 4.5 grams of sodium chloride. So again, you could kind of use it as a conversion factor if you needed to. You could do that for each of these other ones as well. This is essentially milliliters over milliliters. This guy on the bottom here is essentially grams per milliliter, is sort of the units that we see associated with it. So looking at this sort of calculation here, if we prepared a solution by mixing our 2.5 grams of calcium chloride with our 50 grams of water, what is the percent mass to mass? Our calcium chloride is the smaller part here of the solution, which would be our solute. Again, our water here would be our solvent. So the percent mass to mass would be the mass of our solute divided by the mass of our solution times 100%. So very important again in these guys that the mass of the solution is found by adding those numbers together. So 50 plus our 2.5 grams gives us our 52.5 grams, and our percent mass to mass in that case would then be 2.5 grams divided by 52.5 grams times 100% in this case. That gives us something like a 4.76% by mass sodium chloride solution. Question on that calculation. I think we did this one before in an earlier chapter, if I'm not mistaken. I hope. Any questions on that particular one there? Okay, so looking at another one, sort of example of our percent mass to mass composition here. If we made a 37.2% by mass hydrochloric acid solution, and we wanted to calculate the percentage, or sorry, we want to calculate how much HCl there was in 35.5 grams of the solution, again, we can use our percent mass to mass. You can plug and chug into this equation, or again, you can sort of use the percentage as sort of a conversion factor. So if we have something that is 37.2% by mass HCl, what that would mean is essentially you would have 37.2 grams of HCl in 100 grams of solution. Again, just assuming 100 so all the numbers stay the same. Or you could use it opposite way, 100 grams of solution you would have 37.2 grams of HCl. So if we did this more like a dimensional analysis sort of approach, we have 35.5 grams of solution in this case. We could start with that 35.5 grams of solution. And again, we're just kind of doing it like a conversion problem. To get rid of the grams of solution, we would want to use sort of this as our conversion factor, which would give us 37.2 grams of HCl and 100 grams of solution. Grams of solution will cancel, will leave us grams of HCl, and it looks like we get something like 13.2 grams of HCl in this particular case. Again, it's the same thing if you plugged and chugged into here the 37.2 and the 35.5 and solve for this. You're basically doing the same math. It'll come out the same. Any questions on percent by mass or mass to mass or mass to volume, volume to volume? Really, it is the mass to mass is usually the only one that you sort of has to worry about in terms of that bottom number. You want to make sure you do get that solution and not just the solvent, which is a common mistake. Any questions on that there? So continuing on with some concentration units here. Here's one that we have not talked about, I believe, before. This is molality. So this is not molarity. So to emphasize that, molarity is big M. So I'll just write big M. Molarity is moles per liter, like we talked about. This is actually molality, which is small m. Yeah. And it is moles of solute per kilogram of solvent. So the M here is not mass, is actually molality. And again, very much like molarity in that sense, numbers are oftentimes given like 4.5 little m sodium chloride. And again, you oftentimes want to kind of convert that little m into both of the units so that you can see them, kind of like what we do here with molarity, converted into moles per liter when we do calculations, so you don't forget kind of where this goes. So that is moles of solute divided by kilograms of solvent, which is the molality, not molarity. So why don't you give one a try here and see what you come up with. Calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. Maybe some numbers here. Carbon is 12.01. Hydrogen is 1.008. And what we got there, oxygen, looks like oxygen is 16. All right, take a couple minutes here and calculate the molality. So again, we're looking for the molality, not molarity here. So that is moles per kilogram of solvent, moles of solute per kilogram of solvent. So when we're doing this, we're taking 61.7 grams of our propanol here, and that's this guy. That is going to be our solute. Water here will be our solvent in this particular case. So we do need moles of the solute. So we'll need the molar mass of this guy. So we got 3 times 12.01 for our carbons, plus 8 times 1.008 for our hydrogens, and a 16 there for our oxygen. Looking like we got 60.09 as our molar mass. So we'll use that to convert our grams into moles. So 61.7 grams, C3H7OH. And dividing by our 60.09 grams per mole here, going to get us 1.03 maybe. 1.03 moles. And again, that is our top part here. So we do need kilograms of solvent. In this particular case, we're not given grams, but we are given the volume of water. We also are given the density here of water. So basically, if we take 175 milliliters of water and multiply it by its density, which is 1 gram per milliliter. I think I could do this math. That's going to give me 175 grams of water, which is our solvent in this case. Again, we don't need grams, we want kilograms. So we're going to do that conversion of 1,000 grams in a kilogram in this case. And that's going to give us 0.175 kilograms, which would be the bottom part that we need. So what's left is basically just divide those numbers. So we're going to take 1.03 moles divided by 0.175 kilograms. And that's going to get us, looks like 5.87. And again, in terms of units here, they don't cancel. So 5.87 moles per kilogram is okay. Or again, just like molarity, you could write 5.87 and little m if you like as well. So kind of like how we use the big M, you could also do that here with molality. Question on molality.
Why do we have, or why do we not add the grams of the C3H7OH to the grams of water as the solvent?
Yeah, so in this particular one, the molality is actually moles of solute over kilograms of just the solvent. So that's actually what molality is. And that's different than what we saw earlier where we were looking at, where does that go? This guy. So this one, which is percent mass to mass, is sort of a different concentration unit. And on that one, we want the mass of the solution on the bottom. So that's why if we were calculating something like percent mass to mass of this guy, we would want to add it together. But because of molalities actually on the bottom there, just the kilograms of solvent, that's the only thing that we need on the bottom.
Thank you.
Yep. Other questions? By the way, since we're looking at this, sometimes you do need to sort of go between these two concentration units. And really, what sort of ties both of these concentration units together is density of the solution, usually. So, usually, density is sort of the thing that allows you kind of to go from molarity to molality or molality to molarity. So, if you happen to come across a problem somewhere where you kind of need to go from one to the other, it's usually the density there that's sort of that binding part of that calculation that allows you to kind of go from one to the next, because density would be grams per milliliters of the solution, right? So that allows you again to sort of get from our kilograms of solvent to solution, and also you could use it to go kind of backwards to get to the kilograms of solvent. So in case you ever need to go between those, look for density. That's usually sort of the thing that binds them both. Other questions on this? Okay, so a couple of these guys we have talked about before. Again, mole fraction we saw when we were talking about gases. And remember, to calculate the mole fraction is represented by that X. And that X basically means that we take the moles of whatever we're interested in divided by the total moles. Remember here, it's not a percentage, so we don't multiply by 100 or anything like that. We just divide it, get like a point something type number. So we've seen that before, and I think we probably did this problem before, so we'll just kind of look at it again here. We wanted to calculate our mole fraction of methyl alcohol in a solution that's composed of 0.328 moles of our methanol and our ethanol. Here again, we would take the moles of our methyl alcohol and divide it by the total moles, gets us our 0.261, which is essentially 26%, but we don't typically multiply it. Obviously, as we talked about, if you wanted the mole fraction of the other guy, since it's not multiplied by 100, you can actually take 1 minus it, and that would get you the mole fraction of the other guy, as 1 would represent 100% in this sort of calculation. So that should still be fairly fresh, I think. I think it was on that exam we just took. Molarity should also be hopefully fairly fresh as well. So molarity, as we've talked about again before, is our moles per liter of solution. And as we've seen, we do Can rearrange this a lot of times to solve for different things. So moles divided by molarity is our liters, and very common one is our moles, which is liters times molarity. Remember that that is what you get when you take liters times molarity. We also talked about that when you take milliliters times molarity, you don't get moles, but you do get millimoles. So that is actually what you get there. And that's why, again, not a bad thing. If you then divide by milliliters, you'll get back to molarity. So remember that if you kind of use the molarity by itself in a calculation, you do want to make sure that you convert the volume into liters so everything cancels out correctly. Again, you can, for something like the dilution equation that we saw, leave the volume in milliliters. As long as you're dividing by milliliters, it'll all come back to molarity at the end. So these are some different sort of units of concentration that we talked about, some previous chapters, some here with our molality. And some of this stuff is going to be important for the next sort of topic we're going to talk about involving solutions. And that is what is referred to as colligative properties. So colligative properties are basically properties of solutions that are essentially based upon how many particles are essentially floating around in that solution. So the idea here is if you have, say, a container of just a pure solvent, say something like water, right? Got some water molecules here. Now, in a pure solvent, if there's nothing else in there but water, it's going to eventually, at a certain point, start to boil, right? So our water molecules are kind of free to hit to the surface and boil. It also can, if you kind of drop it down at its freezing point, these guys can pretty much kind of come together and freeze at that point. Now, what happens though if we dissolve something in water? So if we take our water here and we actually will dissolve something in it, say like sodium chloride or something like that. So in our water, we have our water molecules are represented by these circles. We got some water. And maybe we pop in there some sodium chloride. So we got some sodium ions floating around, some chloride ions floating around, you know, along with our waters. Now, when we get to a point where we're at, say, the boiling point or something like this, as we start to heat this thing, wonderfully drawn Bunsen burner there, as we heat it, also known as a triangle, I think. As we heat this, these water molecules, they got things in their way. So it kind of takes them a little bit longer to get to the surface. There's more things they got to kind of break apart from. So it's going to take a lot more energy to kind of get those water molecules to be able to escape the surface, dropping back down. So there is sort of a formula here that we could calculate sort of the vapor pressure, sometimes referred to as Raoult's law. This is PZ, which is the vapor pressure of the component. X is our mole fraction, like we were just talking about and we've calculated before. P naught Z is the vapor pressure of just the pure substance, obviously like the pure solvent, for example, or something like that, are the pure substance. So the vapor pressure lowering may be defined as the vapor pressure of the pure substance minus the vapor pressure of the solution. So the idea here is, again, we got a lot of particles sort of in the way. And as that, what that means is it's going to take a lot longer or harder for those guys to escape into the gas phase. And because there's going to be less molecules under sort of normal conditions that can escape into the gas phase, we're going to have less vapor pressure above that liquid because there's going to be less guys that can do that compared to if you just had, say, the pure substance by itself. They're kind of free just to escape. We're going to get a greater amount of gas molecules above that liquid. So let's take a look at a problem here involving vapor pressure. The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol if we throw some glucose in there. And we dissolve it in 1.2 moles of the alcohol. So if we want to figure out the Vapor pressure of the alcohol in this solution, we need to figure out the mole fraction of the alcohol. So we know we have 1.25 moles um, divided by 1.45, and that gives us a mole fraction of 0.862. Now we can calculate our vapor pressure by multiplying those two. And what we see is we end up with a vapor pressure in that solution of 57.3. And what we see is the vapor pressure goes down in this case because of that. So what we have again in this situation is just the sort of ethyl alcohol by itself in this solution. It's kind of free to kind of go like it normally would. It will create a certain amount of vapor over there that represents 66.5 torr. By dissolving that glucose in there, we now have all these kind of glucose molecules that basically get in the way. And again, it's going to create less gas molecules above that liquid. And we do see that it does come down to 57.3 torr in that particular case. So that's one effect of having a lot of stuff sort of dissolved in the solution, is going to affect the sort of natural escape of those molecules into the gas phase. Another effect of stuff being dissolved in a solution is it really does affect the freezing point. And again, instead of allowing sort of the solvent to come together like it normally would, like water molecules coming together to freeze, we got all these other particles basically in the way. So the addition of solute particles in a solution will result in our freezing point decreasing, or having a freezing point depression. So what that means is, again, for example, something like water, instead of it freezing at 0 degrees Celsius, it may actually freeze a little bit lower. Like if you take some rock salt, some ice, right, in those videos where you can just make ice cream right at home in a plastic bag, right? Again, it's going to lower that freezing point of water, going to freeze at a lower temperature, going to allow you to make some at home ice cream. We can calculate that by this formula here. This is the freezing point depression formula. That's the change in freezing point temperature. So that's what that is. That's the change in freezing point temperature. And that's an important thing to remember. It is actually not necessarily the freezing point, it is actually the change that occurs for where the solvent normally freezes to where it will freeze in this situation because of everything that's dissolved in there. Kf is a constant. It is a freezing point constant. It is a value that you look up in a table. And the important part about Kf is you will not find your solution in that table. When you look up the value for Kf, it is all about the solvent. So that is what you're looking up when you look up in the table. So if your solution is aqueous, there's probably a pretty good chance that your Kf value is going to be for water. If some other solvent is used, then obviously you want to look it up. So sometimes people run into trouble because they go to the table, they try to look up the value for the solution they're dealing with, and they won't find it. So again, it's the solvent. And M here is our molality that we were just talking about. So M is our molality, which is our moles per kilogram of solvent. Now, another really important thing to remember when you're dealing with freezing point depression is what we see here. Because the solution will actually freeze at a lower temperature, it's important to know that the change in the freezing point temperature is actually the temperature where the solvent will normally freeze minus the temperature of where your solution will freeze. While this relationship, or why this relationship is important, is because it will allow you to get the correct sign. So if you don't sort of do it this way, you might get the right number, but you might not get the right sign. So instead of you saying, hey, the solution freezes at minus 3 degrees Celsius, you might say it freezes at 3 degrees Celsius. So again, this relationship is really important. What it's going to really allow you to do is either subtract when you should subtract or kind of add when you should add. So freezing point depression, solvent minus solution in terms of the temperature is a really important part of it. Any questions on that one there?
Would KF be found on a table?
It would be. We're going to see that table in about 2 slides, and that value is in that table. And again, like I said, the important part about that is to make sure you look up the solvent when you go to that table. And also, as we'll talk about in just a second, when we see that table, remember that the solvent doesn't always has to be water. So when we think about these things, we oftentimes think about water as always a solvent. And a lot of times we have in our head the normal boiling point and freezing point for water, which is 0 and 100 degrees Celsius. And as we'll see, obviously on the table, if you're not using water as your solvent, you will also have different KF values, KB values, as we'll see in a second, but you'll also have different boiling points and freezing point temperatures. So you don't always want to use 0 and 100, especially if you're not using water as your solvent. So that's, again, another important thing to remember. So let's talk about the other sort of thing that happens that affects boiling point. So unlike freezing point, where it kind of gets it away from the freezing, it lowers that temperature at which it freezes. The opposite sort of happens with our boiling point. It actually increases our boiling point. Again, as I mentioned before, there's a lot more stuff in the way as those guys are trying to escape the solution. So it takes a little bit more energy to get them through all that sort of maze of guys floating around in the solution. And what we typically see is an elevated boiling point in this case. And that's sort of, for example, antifreeze kind of does that. Actually, antifreeze does both. It actually lowers your freezing point and increases your boiling point. So if you live in a really cold area, the water in your car doesn't freeze. If you live in a really hot area, it doesn't overboil. So actually, antifreeze does both things. And we have a very similar formula here that we do for our freezing point temperature. The difference is it is the change in the temperature of the boiling point here. So this is again the change in the boiling point temperature. Again, not the actual boiling point. KB, just like KF, is a boiling point constant, and you again will look this up on a table as well. And just like KF, it is all about the solvent. So that's again what you want to look up on this table. The little m here is again still our molality, which is our moles per kilogram. The difference though is here with our boiling point is our boiling point is actually going to be elevated, which means our solution will actually boil at a higher temperature than our solvent. So the important part in terms of getting sort of your correct sign so that you add or subtract correctly is the change in our boiling point temperature. And this one is actually the temperature of the solution minus the temperature of the solvent. So sort of opposite of a freezing point, you want to take temperature of the solution minus the temperature of the solvent. That again is going to get you to the right adding part or subtracting part when you're actually trying to figure out, what temperature does it boil in this particular case. Any questions on this? So these two formulas. What's your question? Yeah.
I was just gonna ask. So is KF just opposite of KB?
Yeah. So it's not really the opposite of it. It's just two similar type constants, except one obviously deals with freezing, one deals with the boiling point, basically. So really with the KF, we're talking about really that, kind of transition between sort of solid and liquid, and sort of KB is what happens at the boiling point as we go from liquid to gas. So they're not necessarily related to each other like you may be thinking Ka times Kb equals Kw or anything like that. So they're not related to each other sort of in that relationship. Other questions? Now, these two that we see here are actually for what we sometimes refer to as non-volatile solute. That is a fancy way for saying basically molecular, so no ions. And we'll see what happens when we do introduce ions, or ionic sort of guys that dissolve. But this right now is just for things that basically, when they go for a swim, if you're going to dissolve it, something like sugar, when it goes for a swim, it just stays as one whole sort of particle together. So this is a table, and again, not necessarily the one from your book, but you have a similar table. And as you can see, what's listed here is really different solvents. And as we talked about before, we do have water, which is a very good solvent for a lot of things. But again, if we were dealing with something that's nonpolar, this guy here, which is benzene, is nonpolar. This is carbon tetrachloride, which is also nonpolar. Those guys are also really good for nonpolar things. And for our water, our normal freezing point is 0. The Kf value is 1.86, which you see a lot, 1.86. And the units here are degrees Celsius over molality. And that is for our freezing point, while our boiling point for water is at 100 degrees Celsius. That's where it normally boils. And that's 0.512, also degrees Celsius over molality. But as I mentioned before, for example, if you were dealing with carbon tetrachloride, it would have, obviously, as you can see here, different Kb and Kf values. And just as importantly, you can see carbon tetrachloride, its freezing point is minus 22.9 degrees, and its boiling point is 76.7. So again, if you're not using water, make sure that you are using the correct either boiling point or freezing point, depending on sort of the problem that you are doing. All right, so let's take a look at some of this here. So why don't you take a second here and try to calculate the freezing point of a 1.7 molality aqueous ethylene glycol solution. So see what you come up with here. This is obviously dealing with freezing point, hence the words here. We have the molality given to us, so we don't actually have to calculate it, which is kind of nice. Also, we know the solvent is water because it kind of says aqueous here, so that's a pretty good hint that it's probably going to be water as our solvent in this particular case, which is why we would go to our table there and find the Kf value for water. We will also know that hopefully the normal freezing point there of water is going to be 0 degrees. I gotta try that again. 0 degrees Celsius. That's a very badly written one. So that's going to be 0 degrees Celsius is our normal freezing point there for our water. So we could use our freezing point temp equation here, which is our change in freezing point temperature is equal to our Kf times our molality. So in this case, we actually have both, so we could just plug it in there. And if we do that, we got Kf, which is our 1.86 degrees Celsius over molality, times our molality, which was given to us. Again, the molalities are going to cancel. That's going to leave us degrees Celsius, which is good since we're looking for a temperature here. So we got 1.86 times 1.7, going to give us something like 3.2 degrees Celsius. Now, this is where sometimes people make a mistake and they box this as their answer. This, again, is not the answer. This is actually the change in freezing point temperature. So what we're looking for is the actual temperature at which this solution would freeze. So that's why it's important to remember this relationship that we talked about earlier, that the change in freezing point temperature is going to be the temperature of the pure solvent where it freezes minus the temperature of the solution. That means that the temperature of this solution would be the temperature of where the pure solvent freezes minus the change in freezing point temperature. And again, that means that the normal solvent freezes at 0 degrees Celsius minus our change in freezing point temperature, which is 3.2. That is how we get to a negative 3.2 degrees Celsius. And that is less than the normal freezing point of just the water. Again, if you actually box this as your answer, the 3.2 without the negative, your freezing point temperature actually went up, which would be wrong. So that's why, again, it's important to remember that relationship. That's how you're going to get to sort of the correct sign for what you're looking for. Any questions on that? So water here by itself, normal will freeze at 0 degrees Celsius. You throw a little bit of that ethylene glycol in there, it will actually need to go all the way down to minus 3.2 before it starts to freeze. Any questions on any of those steps there? Okay. All right, so why don't you try another one here, I think. Calculate the molar mass of a compound if a solution of 12 grams of it is dissolved in 80 grams of water and it freezes at minus 1.94 degrees Celsius. So why don't you take a moment here and see what you come up with. You are looking for molar mass. So think about units. This is grams per mole here. Yeah? So that is what you're looking for. And again, since we're using freezing and water, Kf is going to be the same as what we used in the last one, 1.86 degrees. Okay, so again, we're using a freezing point here. So we'll use our formula that we saw. Now we're looking for molar mass here, which is grams per mole. And we actually have the top part already given to us. So we're going to take 12 grams of this substance here and dissolve it. So that actually is the top part. So really what we need to figure out is the moles part. And that's actually going to come from sort of the freezing point information that's given to us. Again, we're dissolving it in water. So we know the Kf is 1.86. We also know that it freezes at minus 1.94. So again, a very common mistake some people may make is they'll just throw this right into here. And again, that is actually not the change in freezing point temperature. That is the actual temperature of where it freezes. So we do want to actually use our change in freezing point temperature is our temperature of our solvent minus the temperature of our solution. Again, our solvent, which is water, normally freezes at 0 degrees. This particular solution freezes at minus 1.94 degrees Celsius. And that is how we get to a change in freezing point temperature of positive 1.94. So again, there's a lot of negatives and positives in these problems you got to really watch out for and not kind of put those numbers right in there. What we really have right now is the change in freezing point temperature. We have the Kf. That is going to allow us to solve for the molality here. So to solve for the molality, that will be our change in freezing point temperature divided by our Kf in this case. That's going to give us 1.94 degrees Celsius. Again, positive because we solve for it that way. Our Kf being 1.86 degrees Celsius per molality. Degrees Celsius will cancel. Molality will come to the top there. And that's going to give us 1.94 divided by 1.86. That's going to give us something like 1.043 molality here. And remember that this number is not moles, that is molality, which is moles per kilogram of solvent. So this is basically moles per kilogram of solvent. And remember, we want just moles here, so that's where the last piece of information is going to come from. We have 80 grams of water, which is our solvent. So if we take 80 grams and convert it into kilograms, 1,000 grams in a kilogram, going to move that over 3 places, so that's 0.08 kilograms. We now can times our molality by the kilograms of our solvent, which is our water. The kilograms will cancel each other out. And this again is how we're going to get to our moles part of it. And if we do that, it looks like we got 0.0834 as our answer here. 0.0834 moles. That is the bottom part that we need for molar mass. Any questions on that part of the calculation there? So what's left to calculate is the molar mass, since we have both numbers. The molar mass will be our grams divided by moles. So we'll take our 12 grams that we dissolved of it, divided by the moles that we were able to get from the freezing point information. Again, no units will cancel out here. We'll be left with grams per mole. And if I actually punch the right number in there, try that again. About 144 grams per mole would be our molar mass. Any questions on any of those steps there? So again, we're using our freezing point information to figure out the moles. And we're again solving for something a little bit different than, say, freezing point temperature or something like that. Here we could use this information to help us figure out something like the molar mass. And what that molar mass is whatever we dissolved in that solution. So that's the molar mass of whatever we kind of dumped in there. All right, why don't you try another one here? Why don't you do this one? We'll do some boiling point here. So how many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that boils at 105 degrees Celsius? So here we're actually using our boiling point. So give it a go, see what you come up with. And I'll give you the KB for water, which is, I believe, 0.512 degrees Celsius per milliliter. Clearly, the normal boiling point is 100 degrees Celsius here. All right, take a couple minutes, see what you come up with. Kind of working the same way. We got some information given to us. We have where the solution actually boils. We also have the KB. So from that information, we can pretty much get to our molality, which will help us. So why don't we start with where the solution actually boils. And remember that that number given to us is actually not the change in the boiling point temperature, but where the solution actually boils. And remember that the boiling point is a little bit different. It is the temperature where the solution boils minus the temperature where the solvent normally boils. And in this case, that means that we would have 105 minus 100 in this case, giving us 5 degrees Celsius as our change in boiling point temperature. So we don't want to use the 105 here. We do want to use just the 5 in this case. So again, make sure that you kind of don't miss that part. At this point, we could solve for molality, which would be our change in boiling point temperature divided by the KB, which we would find in the table. Again, for water, which is our solvent. So we would have 5 degrees Celsius divided by our 0.512 degrees Celsius per molality. And that's going to get us 5 divided by 0.512. Looks like 9.77. Again, this is not moles, but this is actually molality. And that means that that is 9.77 really moles of C2H6O2 per kilogram really of water in this case. So we're really interested in how many grams of this guy. So that is where our sort of mass of our solvent is going to come into play. We're going to multiply it. In this case, it's already in kilograms, so that works out nicely. So the kilograms of water or solvent will cancel, and that tells us in the solution we basically have 9.77 moles of C2H6O2, which is our solute in this case. Any questions up to that point? At this point, we want grams, so we need to go to the periodic table there, calculate the molar mass, and it looks like it is something like 62.07 grams per mole when you calculate it, C2H6O2. Moles will cancel, and it looks like perhaps we end up with here about 606 grams of it. Of our C2H6O2. We should probably do some sig figs or something, probably 2 based off of that number there in the calculation. So probably would end up at something like 610 grams of C2H6O2. Any questions on that calculation there? So really a lot of people do sort of mess up that part with the temperature aspect of it. They just kind of go with the actual solution instead of the change when they're using these formulas, and they do usually end up with some trouble on that. Any questions on that particular one? Okay. Then let us take a look at another one here while we're on a roll doing a bunch of these. Let's calculate the boiling point of a solution that's made by dissolving 1 gram of glycerin and 54 grams of water. Again, same values that we've sort of used before. Our KB. Since we're getting to the end here, so obviously we're dealing with boiling point, so should think about our boiling point formula here. We have glycerin, which is our solute, also molecular here. Again, not ionic here. We do have our KB that we could look up since we are using water as our solvent. So we have the KB value for water. We can figure out our molality here in this particular case. So since this is our solute, that's our solvent, we could actually calculate the molality. So to calculate the molality, again, it's going to be our moles of solute over kilograms of solvent. So we do want to calculate our moles. So we're going to take our 1 gram of C3H8, I hope, O3. We're going to use the molar mass from the periodic table. So it looks like if you do all that, add that all together, something like 92.09 grams per mole. In this case, we're going to divide by the grams so that we end up with moles. And it looks like we end up with 0.010, we'll call it 86 moles here of our solute. And that's the top part that we need for our molality. Bottom part is kilograms of solvent. So we want to convert our grams of water into kilograms. We can move the decimal place 3 places to the left, and that's going to give us 0.054. So the molality here would be 0.01086 moles divided by 0.054 kilograms. And that's going to get us looks like perhaps 0.2011 as our molality. Now that we have this and we have our KB, we could actually calculate the change in boiling point temperature, which would be 0.512 degrees Celsius per molality, which is our KB from the table, 0.211 for our molality. Gets us something like 0.103 degrees Celsius. Again, important here that this answer is not where this solution will actually boil. This is the actual change in boiling point temperature. So again, that's where this relationship is important. This is our boiling point elevation, which means it should be the temperature of our solution minus the temperature of our solvent. So we have 0.103 degrees Celsius equals the temperature of our solution minus the normal boiling point of water, which is 100 degrees Celsius. This is important because that's going to tell us we need to add the 100 to the other side. And that's going to give us the temperature of the solution will actually boil at 100.103 degrees Celsius. I guess you could round that down a little bit to probably 100.1 degrees Celsius, just slightly above the normal boiling point of water in this particular case. Any questions on that calculation there? So again, very important not to confuse the change in either freezing point temperature or boiling point temperature with where the solution actually freezes or boils. Any questions on that one there? Okay, we will lay it up there for today. This lecture, sort of. We're going to continue lecturing in lab and finish the rest of this chapter because there's like an exam coming up next week, I think. So we will finish this up, and then we'll talk about what lab we'll do today, and that will maybe be helpful for the exam. So we'll take a little break. We'll meet up at 7:15.